In this lesson, we are going to take some pieces of information from our function and sketch the polynomial graph. So we want to do this without a calculator, and we need to start off with one of the a fundamental theorem, and it's actually called the fundamental theorem of algebra. So here it is. The fundamental theorem of algebra states a polynomial function of degree n has n roots. In other words, whatever the degree of the polynomial is, that tells us how many total roots there's going to be. You can't have any more than that, and you're not going to have less. Now, the roots could be irrational, they could be imaginary, or they could be rational, but the total amount is going to be equal to the degree of the polynomial. So we also have what we call the factor theorem. And what the factor theorem says is a polynomial function of degree n can be factored into n factors. Again, those factors could be real or they could be imaginary, but you will have n of them. They could be double roots, triple roots, but in the end, the total number of factors is going to be equal to the degree of the polynomial. So what that looks like is if I have p of x, here's my polynomial function. I can break this up, and my general expression will look like this. I could have some constant value, k, and then I break up every degree into factors. And depending on how many, if you have an nth degree polynomial, you're going to have n factors. So for example, if I have, let's just say we have a degree of 3, and my factors are x minus a, x minus b, x minus c, like that. That means I have roots, or let's call this x plus c. That means the roots are just like when I find the roots of a second degree. I do the same thing. The roots are going to be the value when you set each factor equal to 0. So x minus a is equal to 0, so there would be a root at a. X minus b is equal to 0, there would be a root at b. X plus c is equal to 0, there would be a root at negative c. So the roots, the solution set would be a, b, and negative c. You know, the roots of a second degree equation, those are the x-intercepts. These are the same thing. These are going to be x-intercepts on my polynomial function. So that's what we're going to use to sketch the graph. We're going to find the x-intercepts. And then also do a couple other things just to do a rough sketch of the graph. It won't be perfect. We really need calculus to get it really good, but we can get a rough idea of what this function looks like. So here's an example we're going to work. I want to sketch the graph without a calculator. P of x is equal to x minus 3 times x plus 2 times x minus 1. We actually want it in factored form, so we're not going to multiply this out. And that's actually our first step, if it isn't already factored, is to actually factor the polynomial to find the zeros. So we want to break up this and set up each factor equal to 0. If you look at it, if I were to multiply out all my front terms, I would have an x cubed. So this is a third degree function, has a degree of 3, and that means I'm going to have 3 roots, whether they're real or imaginary or whatever. It's already factored, so I set each factor equal to 0, and I solve for the roots. I have a root at 3. I have a root at negative 2, so x is negative 2, and I have a root at positive 1. So those are my zeros. That's where they cross the x-axis. 3, negative 2, and 1. So that's the first step. The next step is to get another data point on this graph, and that's to find the y-intercept. Basically, that's evaluating p of 0. When x is 0, you're sitting on the y-axis. So if we do that, p of 0 in this case is going to be 0 minus 3 times 0 plus 2 times 0 minus 1, which means you get negative 3 times 2 times negative 1. P of 0 in this case is going to be 6. The next step is to determine the end behavior of the function. I need to know where my ends are going to go. So looking at my function, it depends on the sign and the exponent of my leading term. Well, this guy's all factored out, but if I were to find my leading term, it would be what you get when you multiply all of my variables and any coefficient in front. If I do that, if I multiply all the first, so x times x times x, my leading term is x cubed. So x cubed, if I apply the end behavior, as x approaches positive infinity, my y value is also going to approach positive infinity. As x approaches negative infinity, if I raise a negative value to an odd exponent, I'm going to get a negative value out. So y is going to go to negative infinity. That means I'm going to be, as I keep decreasing, my ends are going to be in the third quadrant and the first quadrant. So now we just sketch the graph. That's my fourth step, using all this information that we have. Again, it's a really rough sketch. We need a little bit of calculus to make it any better, or we would create a table of values to get more points, but we don't need to do that right now. We just want to do a rough sketch. So here's my y-axis and my x-axis. I know I have, it crosses the y-axis up at 6, because that's P0. And then I have the roots I'm going to put in. So I'll put those in. Let's see, I got a root or a 0 at 3, and I got one at -2, and I have one at 1. Now I know I'm going to come down from the third quadrant for my end behavior. I'm going to come up like this, and at some point turn, and at some point turn, and end up with something like that. That's a really rough sketch. I don't know how high it goes. I don't know where the turning points are right now, but that's just a rough sketch of what it might look like. My arrows indicate the end behavior that I figured out over here. As x is positive, this is a first quadrant end, and this is a third quadrant end. So that's what you need to show. And you do need to show me all this work in order to sketch the graph. So I just want to add one more kind of complication to this thing, but it's really not bad. If I have something like this, x plus 1 times x minus 2 quantity squared, we know that this guy is a double root. So when you have double or triple or multiple roots, your graph behaves a little bit differently than if they were all just single roots. And it really just depends on whether this exponent is even or odd. So here's what happens when we have an even exponent. If a factor is raised to an even exponent, like this one here, if it's a double root or a fourth root or whatever, the graph is going to turn at the corresponding root, just like a parabola, just like the turning point of a parabola. It'll touch and then turn the other way. So if the exponent of the factor is odd, then the graph is going to cross at the root like you would normally expect. So that's what you have to look out for. You have to look out for these conditions. An even root is going to have a turning point, or an even exponent is going to have a turning point at the root. An odd exponent is going to have the graph just cross at the root. So we'll work an example that looks at this condition. Here it is. We're going to sketch P of x, which is x minus 1 cubed and x plus 2 squared. So the first thing we should try to figure out is what is the degree of this function. If I were to write all these things out and then multiplying all the front terms together, this guy would produce an x cubed, and this guy would produce an x squared, so x cubed times x squared. This is an x to the fifth. So this is the term we use to look at end behavior and to figure out how many roots do I really have. I should have 5 roots. But if you look up here, I have a triple root here and a double root there. So my zeros, or my roots, I'm going to have x equals 1, and that's actually a triple, and x equals -2, and that's a double. So when you think about what's going to happen with this guy, since this is a double root, since my exponent is 2, he's going to turn there. He's going to turn, and this guy's going to cross when you do your graph. So we got to find the other two things. We got to look at end behavior. And end behavior when it's x to the fifth, as x approaches positive infinity, y is going to be positive. When x is negative, because it's an odd exponent, y is going to be negative. So again, we're looking at the first quadrant and the fourth quadrant. Okay, and then we need to figure out p of 0. P of 0 is going to be 0 minus 1 cubed times 0 plus 2 squared. So that's negative 1 cubed times 2 squared. That ends up being negative 4. So P of 0 is negative 4. So I have all my work shown, like you need to do. And now I'm going to sketch the graph. Let's see, I know I have an important point at negative 4. I know I have a point at 1 and a point at negative 2. So I'll put those points in. There's P of negative 4, positive 1, and negative 2. My end behavior means I'm going to be down like this and up like that. So I'm going to cross at 1, and this is a double root, so here I'm just going to turn. Here's what this looks like. You're going to come up, and instead of crossing, you're going to turn, go back down, turn somewhere, and then come up here like that. I have no idea exactly where this would turn. You could put in some test points if you really wanted to know, or later on when we get into calculus we'll be able to find that point. But this is the critical stuff. You need to turn it here, you need to cross it here, and then put in P of 0 and have your end behavior be correct. And that's really all you need to do at this point. We'll add more on towards the end of the year when we get into that kind of stuff. Or if we don't get into it this year, you'll be doing that next year. So that's these are examples of what you're going to see in class when we sketch polynomial functions. It's important to show your work. You need to show me the zeros. You need to show me end behavior and how you get P sub 0 if you're going to get full credit when I grade these things.